Hello everyone, welcome to the next lecture for Geography 101. Today we're going to be talking all about wind and atmospheric circulation in general. So for this audience, I know many of you from New Jersey here don't need me to harp on the reason why knowing about major storms and wind are important to your everyday life. New Jersey was hit by Hurricane Sandy and caused widespread flooding and wiped out hundreds of thousands of houses. The storm itself caused 233 deaths, over $80 billion in damages, and the storm was pretty unprecedented. It had wind speeds over 115 miles an hour and pressures down to 0.93 atmospheres, which made the storm surge particularly bad. And on top of the fact that the storm happened at high tide, there was widespread flooding all over the state. So knowing about atmospheric circulation and wind are definitely important, and knowing the phenomena that cause these different events are really important for making sure that we reduce the amount of damage caused by these storms. Hurricane Sandy was far from the last storm that New Jersey has or will encounter. Just the last few days ago, we had Tropical Storm Cristobal, which hit Louisiana and caused widespread flooding. And that's far from the last hurricane that we're going to see this season. It's expected that this hurricane season will be historically bad, and more strong hurricanes are yet to come. This is in part because climate change. Climate change provides more energy, more heat to these storms. And the more energy they have, the stronger that they are, and the more severe damage that they can cause. And climate models have shown that we should expect more major hurricanes to make landfall in the future due to climate change. But let's take a step back and just talk for a second about what is wind. So wind is the movement of air from high to low pressure. So you can see here that you have a bunch of atmospheric molecules bouncing around, the high density, and that's an area of high pressure. And because they're all bouncing off of each other, they're bouncing off into this area of low pressure. And so air will always move from high to low pressure. And you can see that here as well in the top-down view, where you have this area with higher millibars with wind moving to the lower pressure area. So we measure wind in a number of different ways. The most common being an anemometer. This here is an anemometer located on top of a weather station. This is a cup anemometer that spins as the wind blows. And then this would be a wind vane or a wind direction measuring device, which tells where the wind is coming from. So the wind speed can be measured in miles per hour or kilometers per hour or meters per second, and then the direction is in degrees. But we can also categorize that wind speed. The Beaufort scale is a scale that goes from 0 to 12. That's a nice way of being able to categorize different wind events in terms of the damage that they can cause. So 0 being completely calm and no damage expected, to all the way up to 12, which is hurricane force winds. And you could say, for example, this particular storm was a Beaufort scale 7, and it was causing trees to move and resistance while walking. Another way that we represent wind is through wind maps or barometric pressure maps that you can see here. Barometric pressure is just the pressure in the atmosphere. It can be measured in millibars or atmospheres or millimeters of mercury, and they're represented on the map through isobars. So isobars are lines of constant pressure. For example, these gray lines here are isobars, and they represent a constant value of pressure all along that line. And so the wind will always move perpendicular to the isobars, and the strength of that wind is determined by how close together those isobars are. So on the map, if you see isobars that are very closely spaced together, you're going to have stronger wind, whereas here where you have them spaced far apart, you're going to have slow-moving wind. There's a number of forces that act on that wind to drive it to move quickly through the atmosphere. The one that I just described was the pressure gradient force, and that's the force that's moving air molecules from an area of high pressure to areas of lower pressure, perpendicular to those isobars. And vice versa, it's the same force that's causing wind to move towards areas of low atmospheric pressure. The other effect or force that's acting on the wind is the Coriolis effect. And if you remember, we mentioned that briefly in the couple lectures ago, but we'll go into a little bit more detail here because it has a big effect on different atmospheric circulation patterns. And so the Coriolis effect says that because the Earth is rotating and because the area around the equator is further from that axis of rotation, then the atmosphere and the mass that's near the equator has to move faster to make it all the way around that axis of rotation. So atmosphere that's near the equator is moving faster to the east than atmosphere that's closer to the poles because it has further to go for each rotation of the Earth. And that has the effect of the air molecules moving relative to each other whenever they're changing latitude. So, for example, if you had a parcel of air near the equator and you moved it southward, that fast-moving air near the equator is going to be moving faster than air that's further south of it, and so it's going to look like it's turning to the east. And so whenever you move away from the equator, you're moving that the parcel of air is moving relatively eastward. And the opposite is also true. So if you have a parcel of air and you're moving it towards the equator, that air is encountering air that is faster eastward movement than it, so it's going to appear as if it's moving westward. So poleward air moves eastward, equatorially moving air moves westward. And so these two forces act against each other. And we can see that here with geostrophic balance. Geostrophic balance is a condition in which the pressure gradient force is equal to the Coriolis force. And so what that causes is the wind to circulate and be parallel to those isobars because the Coriolis effect is rotating that wind around. And so you see here these red arrows indicate that pressure gradient force pushing that wind away from the high pressure system or towards the low pressure system here. And that Coriolis effect wanting to curve that wind and counterbalance that wind vector. And so in geostrophic balance, which usually occurs higher up in the atmosphere, you have wind circulating around different fronts. The other type of balance is called frictional balance. And so that's when you have a lot of friction in the atmosphere. For example, if you're close to the surface of the Earth, there's a lot of friction as you're moving against the ground. And that's why you have wind speeds that are generally lower, low down in the atmosphere compared to higher wind speeds higher up in the atmosphere. And so you tend to have a frictional balance lower down in the atmosphere. And that causes the Coriolis effect to be weakened. The slower the wind speed, the lower the Coriolis effect, and so the pressure gradient force instead is the predominant force. And we can see that here, where these forces are counteracting each other, but the Coriolis effect is weakened due to friction, and so the pressure gradient force is stronger, and instead of wrapping around that front, the wind is moving away from that high pressure area and towards that low pressure area. And again, that's more common closer to the surface of the Earth. All right, these different forces can cause cyclones and anticyclones. So a cyclone is a low pressure area. So a low pressure area would be caused by the ground here being warmed up and that atmosphere expanding. And as it expands, it moves upwards and it draws in atmosphere from the surface of the Earth, and that atmosphere also moves up. And if you can remember that as you have moisture that's rising in the atmosphere, you have adiabatic processes, and so that causes condensation to occur. So it passes that condensation limit and clouds start to form. So cyclones are often associated with cloudy conditions. Anticyclones are just the opposite. So you have a high pressure system, usually caused by that land being particularly cold relative to the surroundings. And so you have air sinking down from the upper atmosphere and pushing air out near the surface. And so these are generally associated with sunny weather, because instead of condensation happening as air is rising, instead the air is falling and leaving just sunny conditions. So as this air is moving, though, it's circulating. So that's why they're called cyclones, because the Coriolis effect causes the wind to rotate as it's either moving towards the cyclone in the lower atmosphere or away from the anticyclone in the lower atmosphere. And so you can see that here that these systems are rotating around that lower high pressure system. So also remember that the Coriolis effect causes rotation in opposite directions depending on which hemisphere you're in. So in the northern hemisphere, a low pressure front causes circulation in the counterclockwise direction, whereas in the southern hemisphere, that Coriolis effect will cause that wind to rotate in a clockwise direction around that low pressure front. And then for anticyclones, the northern hemisphere, as the wind moves outwards, that wind will rotate clockwise, and in the southern hemisphere, that wind will rotate counterclockwise. And so that's a good way of knowing if you just see a picture of a cyclone, whether it's in the northern or southern hemisphere, just by the way that it's rotating. So hurricanes are just particularly strong cyclones. So hurricanes are always low pressure systems, not high pressure systems. And as they rotate, they're either rotating counterclockwise or clockwise, depending on which hemisphere they're in. So if you see a picture like this, where you can see the arms of the hurricane rotating around in this counterclockwise motion like this, you know it's going to be in the northern hemisphere. Whereas a hurricane like this, where the arms are spinning around this way, indicating that it's rotating clockwise, you know it's in the southern hemisphere. All right, let's take a break and we'll return and talk more about the atmosphere in a second. All right, see you soon.